Hello and welcome to Vital Signs, a podcast about your health, brought to you by Bond University. I'm Matt Webber. Today, an insight into neurological health, treatment of it and research into it. What do I mean by neurological health? Well, I'm talking about conditions like Parkinson's disease, dementia, epilepsy and others. And today in particular, multiple sclerosis. A staggering number of Australians live with a neurological disorder of some kind. 1 in 4 in Queensland, the state where I'm sitting right now, alone. That's why research into neurological health is critical. It's something Bond University is taking very seriously, and more on Bond's commitment to neuro-wellness more broadly a bit later in the podcast. For now though, we're going to meet Jacob Thorstensen. He's a neurophysiologist and researcher here at Bond, an assistant professor at that. And he's just received a research grant from MS Australia to dig a little deeper into the effects of electromagnetic brain stimulation. It's formative work, but when the economic cost of MS alone is something in the order of $3 billion a year to the Australian economy, it could ultimately prove hugely beneficial. I'll let him explain more. Jacob Thorstensen, welcome to the podcast.
Great to be here.
Exciting time for you.
Well, yeah, I'm very excited to get some funding from MS Australia. It's very tough to get research funding in Australia in the current climate. So, yeah, I'm very grateful to be supported by MS Australia to pursue some exciting research avenues in the MS space.
We're going to dig into some detail about MS itself and what it is that you hope for and what you aspire to do with the funding that's been sent your way, and what sort of research you will be undertaking, because that's fascinating in of itself. But I wanted to talk a little about you and your background first, and how you've come to the neurophysiological space. You started off in exercise science, I believe, didn't you?
Yeah, so all throughout high school, I was really into my sports. I played a lot of soccer. And I got to year 11 and 12, choosing the particular subjects I do at high school to get into university. And at that time, I was like, I actually really want to become a personal trainer, believe it or not. And I wanted to do my Cert 3 in Form and Fitness. Went home to my parents, my mum. She sort of said, come on, Jacob, try and give university a crack at least. So we compromised and I studied exercise science. And I thought exercise science would be great because I'm into sports and exercise, but it also gave me a really, really nice grounding in anatomy, physiology, pharmacology, topics like that I could sort of bring forward throughout the rest of my career and whatever I decide to do after that. So I did exercise science, and I initially wanted to do something hands-on with patients, maybe like physiotherapy or medicine, but it would have been around second year or third year in my exercise science degree, I got really, really into understanding how the body works. I thought, wow, this stuff's really cool. It's the most fine-tuned engineering in the world that goes into our bodies and how it works. So I really sort of honed in on more of the mechanistic side of medical science. So I had a particular interest in neuroscience, aka studying the brain and the spinal cord. I thought neuroscience was fascinating, and one of the reasons why I found it so fascinating was because we knew a bit about how the brain and the spinal cord work, but we don't know everything. And I thought, okay, maybe that's something that I can focus on and think about a bit more, because we don't know everything, I might be able to have a bigger impact in that area. So there was a really, really cool and interesting neuroscience lecturer that I had in my exercise science degree. I chatted to him, I said, can I do some research? So that led to an honours degree. The honours degree went well, that led to a PhD degree in the same lab, and then I've never looked back. I've sort of stayed in the neuroscience research space since then. I've then gone on to do a postdoc fellowship and then work as a full-time academic in the neuro space, combining research and teaching. But it all really started off with an interest in exercise science and human movement and how the brain controls muscles and stuff like that.
Are you describing an accidental neurophysiologist?
Well, asked me in high school in year 10 if I was going to be a
Yeah.
neuroscientist with a PhD and working in a medical school, I probably would have laughed because I probably wouldn't have even known what a neuroscientist is and what they do. So,
As an aside, is there an advantage to arriving to these kinds of things later in life with a more fully formed idea of what human beings are? I mean, a lot of kids are sort of on the medical school treadmill from a very young age these days.
for sure.
Is there something to be said for that, do you think?
I think so. I think in a lot of fields of science, it's great to have a big diversity of opinions and backgrounds and perspectives. So I think more of a non-traditional entry into neuroscience in the sense that I wasn't sure exactly what I was going to do from an early age. I think it's great sometimes to have non-traditional pathways into certain programs. So there are some advantages, I think, to that for sure.
It's an interesting area of expertise too, because I think people are often surprised at how close they are to someone who's affected by a neurological problem, whether it's epilepsy or motor neurone disease or multiple sclerosis that we'll talk about in a little more detail. I'm happy to fully disclose my life has been touched by multiple sclerosis on account of my wife's diagnosis a few years ago. She lives very successfully with MS and has managed her health exceptionally well since then. But it's certainly opened my eyes to the fact that this is a critical area of need in the research space simply because of the breadth of ailments and the number of people that it affects. I mean, 1 in 4 Queenslanders, these are figures that MS Queensland, for instance, espouse fairly regularly as part of their pitch to the public. 1 in 4 Queenslanders will be affected by a neurological problem at some point in their lives. 25% of us, that's a stack.
It's massive.
Yeah.
Yeah, I think the nervous system is so finely and precisely engineered until it's not. So I think research has made a great advancement or foray into developing new treatments and, dare I say, sometimes cures for ailments, diseases or disorders that affect the nervous system. So I think research in the neuroscience is really, really critically important to sort of help those 1 in 4 people that come across some sort of neurological ailment in their lives.
I was staggered to learn though, and these are stats quoted from last year, 37,700 Australians are living with MS alone. That's 77.4%. Or a 77.4% increase since 2010. Is that a diagnostic thing? Are we becoming better at recognising ailments and therefore a boost in figures, or are there other things at play that we're not aware of?
I think the short answer is sometimes we're not entirely sure.
Yeah.
I think it's multiple things. I think diagnostics have gotten better. I think just an awareness of certain neurological conditions like MS has also improved and increased. So we're better able to recognise early signs and symptoms of something like MS, which can lead to more timely diagnosis and treatment. So I think it's multiple things at play, but I think we don't entirely know whether there's some environmental thing or factor that's accelerating some of these rates as well. But I think it's just a combination of things. But hopefully future research has some better answers.
Has
for
some
that.
of this covered. Let's focus on multiple sclerosis specifically. I'm well aware of it from my own personal experience, that of my wife. A lot of people would have heard of it via the MS Readathon, of course, a fundraising initiative that takes place every year. But a lot of people may not even know what MS stands for, multiple sclerosis. What is it and how can it be so debilitating?
MS, or multiple sclerosis, is a disease that affects the nervous system. So in our nervous system, we have these cells, they're called neurons. And neurons, they send electrical signals around the body. And some of our neurons, or I should say, most of them, they have this coating around a part of the neuron called the axon, which is the very, very big long bit that sends signals around the body. And that sort of fatty coating is important because it helps speed up the electrical signals that are sent around the body. In MS, there is something wrong with the immune system, and the immune system targets those fatty sheaths, which we call myelin, around our nerve cells, and it breaks them down, it destroys them. So therefore, the nerves or the neurons in our nervous system can't send electrical signals as well as they should.
So it's an efficiency thing.
It's an efficiency thing. And we can see where the nerve cells have been damaged on an MRI. Typically, if we were to suspect someone had MS, they'd go and see a neurologist and they'd be sent for an MRI scan. And on that MRI scan, we can see little white patches in the brain, which we call lesions, and that's because those parts of the brain have been affected by the immune system, which have broken down some of the myelin sheaths in that area.
So that's what it is. What are the symptoms of it? Because I know there's a significant breadth of effects of this disease.
Yeah, I think no two people with MS are exactly the same. So the brain and the spinal cord has many functions. It controls our mood, it controls how we move our muscles, how we take in information from the environment, our senses, and also how we control all the physiology of the organs within our body. So the nervous system does quite a lot. And considering that MS attacks different parts of the nervous system, it can lead to different symptoms depending on where those lesions or effects in the nervous system actually are. So some people with MS might have motor difficulties or dysfunction, so problems sustaining muscle contractions, walking, stuff like that, carrying grocery bags, everyday activities that we'd take for granted usually as people that don't have MS. People with MS will find those things more challenging. They might have things like pins and needles in certain parts of the body, very bad pain in some parts of the body that relates to sensory issues, things like cognitive and attention problems. People with MS might have problems staying focused when they're at work or university, for example, because the MS has affected parts of the brain that are involved in those things. And even things like bowel and bladder dysfunction can be seen in people with MS. So the signs and symptoms are very wide, very diverse, and they're not the same from patient to patient typically.
And when you add up the sum total of that list of symptoms, which is kind of endless, little surprise here, another stat, that the total economic burden of this disease specifically, leaving aside other neurological issues, $3 billion. That's in 2024, so no reason to think why that hasn't gone up in the last couple of years. Everything else has. But that's, if you want to put it in crude terms, that is a really significant chunk of an economy that is required to sustain the health of people who would otherwise struggle. And we're seeing, as I've already mentioned, diagnoses rise. So that's where research becomes critical and funding the sort of work that you're about to embark on. Tell us about how it is that you're going to be spending your research grant.
With MS, we have some treatments at the moment that work well to slow down disease progression because MS symptoms tend to get worse over time. So disability increases the longer someone has MS and is alive. So although there are medications that target the immune system that slow down disease progression, there's not really too much we can do to help someone with MS regain what they've already lost. My background's in exercise science and neurophysiology, so I'm interested in the signs and symptoms, or I should just say the symptoms of MS that relate to motor control. So things like the inability to sustain muscle contractions and to pick up grocery bags and walk around and stuff like that. And also how that leads to things like fatigue that we mentioned before, which seems to be quite prevalent in a lot of people with MS. So in my research, I'm going to try and regain some motor function. And the way that I'll be doing that is I'll be harnessing the ability of the nervous system to change its structure and function. So whenever
So we're talking neuroplasticity.
neuroplasticity. So no matter if you have MS or if you're a neurologically typical person, we all have the capacity to rewire our nervous system, and that's called neuroplasticity. So the individual cells in our nervous system, they change the strength of their connections, and then in some parts of the brain, we can actually grow new nerve cells. What I'm going to do in this project is I'm going to try and increase the plasticity in the spinal cord. So the spinal cord, like the brain, can also learn. And the way that I'll do that is I'll be using magnetic and electrical stimulations. So if I was to go into a bit more detail about what I'm going to do, so it's called transcranial magnetic stimulation. So I can use a magnetic coil that's placed over the part of the brain that talks to the spinal cord and then talks to the muscles, which we call our motor cortex. I can stimulate that to send signals down to the spinal cord. And then if I was to combine that with stimulation of a nerve in the arm or the leg, and if I was to time those signals from the brain, from transcranial magnetic stimulation, with stimulations from a nerve in the periphery at the right time, they'll collide in the spinal cord essentially and then increase the ability of the motor neurons in the spinal cord to respond to signals from the brain. And we think that this approach might be a way to artificially enhance a bit of plasticity in the spinal cord, because the motor neurons in the spinal cord of people with MS seem to be not as affected as if we compare to the cells inside the brain, for example. And because the brain drive to the spinal cord to talk to the motor neurons becomes a bit weaker, we're hoping that this approach, combining brain stimulation with nerve stimulation, will be able to increase the ability of the spinal cord to respond or talk to the signals that come down from the weakened brain in MS.
Jacob, I'm a pretty visual person,
Yep.
and although your very articulate
Yep.
description of what it is that you're hoping to do is welcomed,
Yep.
we have the benefit of your machine being here
Yep.
on campus at Bond.
Yep.
Let's duck over and give it a whirl, shall
Great.
we?
Let's go have a go. So you ready to go?
There I am. Oi!
Can you feel your muscles twitch?
Yeah. Yeah. That's crazy. So talk me through the science of what's happening right
So
now.
essentially what we're doing is whenever I stimulate, we're stimulating the part of the brain that talks to muscles of Matt's upper limb here. So when I stimulate, we're activating the primary motor cortex, which has these big long neurons that travel down the brainstem towards the spinal cord, that then talk to, or what we call synapse with, lower motor neurons. Those lower motor neurons form the peripheral nerves of the arm that go out to the muscles, talk to the muscles. So whenever we stimulate the primary motor cortex, we kickstart a chain of events that go down the spinal cord and out towards the muscles that happens within milliseconds. And we're really bypassing the voluntary control of muscles. We're artificially generating muscle contractions with the magnetic stimulator. So I'll do it a couple more times. How does that feel?
Well, it's not in the slightest bit painful.
Yeah.
It's just a strange sensation. It's
Yep.
you're out of your control.
Yep.
So yeah,
Yep.
you're driving the bus. So
Yep.
I'm not
Yep.
doing that.
Yep.
It just happens. It's
Yeah.
odd. It's quite a strange feeling.
So we're hoping that when we only did a couple of stimulations then, but when we're doing hundreds of stimulations and when we're combining that with stimulation of a nerve that goes back into the spinal cord, if we do that multiple times throughout a session, we're hoping that we can improve some of the connectivity between the brain and the spinal cord to maybe tap into some of the neuroplasticity in the brain and harness that to hopefully help people with MS regain some of the function of their upper limb muscles if we target the upper limb motor cortex.
Fascinating that something so simple could have such a big consequence down the line. That's the hope.
For sure. Yeah.
Okay, so I'm back in the game. perfectly normal, having my nerves stimulated and my fingers tingling and wiggling as a result of the copper coil above my brain. All very painless, really, but hopefully very interesting for you.
Yeah, well, it was good to be able to let you experience what the stimulations feel like. And the important thing is that all of the stimulations with transcranial magnetic stimulation are painless and non-invasive. So with the magnetic field that we pass into the brain that produces an electrical current in the brain, that actually gets through the scalp, and you can't actually feel that because it's a magnetic field. It doesn't activate the receptors on your head that usually respond to signals.
Let's go back to the year 10 version of you, Jacob. Do you ever imagine yourself talking about magnetic fields and the like in this sort of context?
Yeah, maybe in the context of a year 10 physics class.
Yeah, something like that.
Nothing outside of that.
Not this. So how will, we're at very early days. The announcement is literally only a matter of days old, that you've been successful with your grant application. Where does it go from here? I presume you want backsides on seats and patients to contribute to a body of work.
The work that's funded by MS Australia is going to be a pilot study just to see if the technique that we're going to use, combining brain stimulation with nerve stimulation, whether or not that's feasible and whether or not that's safe for people with MS. And we're trying to see whether or not that technique as well actually changes anything when it comes to neurophysiology. Because in the brain stimulation field, sometimes there can be some placebo effects. So when you put a stimulation coil over someone and tell them that you're stimulating them, and you mimic the sound and control for everything else, sometimes psychology can take over and people think that they've been
doing this.
That the magnet's actually doing something to them. So we want to do a very carefully controlled study just to see if it's safe and feasible, and that it actually changes the physiology of our motor pathways in our spinal cord.
So this is very much indicative, sorry to interrupt you, but this is very much indicative of the scale of the problem. Resources do get put towards this base level type of research that is hoped will reap significant dividends down the track. But, I repeat again, the total economic burden of MS reached $3 billion a couple of years ago. This is a significant problem in our society that needs management, and any way to try and kickstart efficiencies for the betterment of the health of patients, of course, but economically as well, it's really significantly important.
Yeah, for sure. So studies like the one that I'm going to do that has been funded by MS Australia, they can hopefully lead to larger clinical trials that will help eventually lead to potentially treatments that real Queenslanders and Australians with MS can go to their neurologist or maybe even their GP or their physio and then use themselves to help them regain some of their functional capacity. So ideally, this line of research, that's the long-term goal. But of course, as you mentioned, there are a lot of steps that we need to cross or cover before we get to that end stage.
So how many people do you need to see?
So we're aiming from anywhere from 20 to 30 people with MS to come in and experience the stimulation. So that will be across 2 sessions. So we'll have a session that has what we call sham stimulation or placebo stimulation, so that we can control for the psychological aspect of things. And then we have a session that is the real stimulation. And all participants that sign up for the study do both the sham and the active form of stimulation. So there's no groups where one group would miss out and they only get the sham stimulation. All participants will have the opportunity to do both arms of the study.
It's extraordinary to me how far we've come, and I mention this often when talking about this particular topic, but if I go back to my childhood, I'm in my 50s now, so we're going, let's go back 30 years or so. And if I think back to then and how multiple sclerosis specifically was defined to me, or how I imagined it, it was literally someone wheeled in on an electric wheelchair or motoring themselves in an electric wheelchair, significantly disabled, selling pins in a shopping centre for the day, and that doesn't seem that long ago. Treatments and therapies and research has really changed significantly in the past few decades, and I'm guessing that makes the neuroscience part of what you do particularly exciting. You must feel like you're really at a cutting edge of something that can evolve quickly.
Yeah, I think there has been an explosion of research into the immune system recently when it comes to MS, and we're getting really close to discovering, what does the immune system actually do when it comes to targeting the neurons in the nervous system. And off the back of that, there have been some really, really cool and effective drugs that target the immune system. But from my background working in the neurophysiology and the neurophysiology of movement, I've always been interested in using non-invasive techniques to study and to modulate the nervous system, including TMS. And in my PhD, I was using TMS to study the motor pathways and how the brain talks to the muscles. But then when I worked, I did actually a postdoctoral fellowship at the Queensland Children's Hospital, and I was working with some kids with really, really severe acquired brain injuries, so strokes and traumatic brain injuries, so kids that have got severe concussions from a sporting accident or a car accident, for example. And there I got the opportunity to actually just tweak the way that I use these brain stimulation devices. Instead of just studying how the nervous system works, I was working with a pediatric neurologist, and we were thinking, okay, can we use these devices to rewire the brain? And now I've taken that forward into the MS space, and I'm hoping that we can make some inroads when we combine or when we use what we call electroceuticals, right? Because that's what it is. It's modulating the brain from the outside with magnetic or electrical fields. Can that be used as an add-on to traditional immunotherapies and physiotherapy and stuff like that? So it's a really exciting space, and I really think that this whole field of neuromodulation, so using things like TMS to really rewire the brain non-invasively from the outside, I think that has applications to many neurological disorders, including MS.
Yeah. Parkinson's, dementia, you name it. It's quite a significant list. You're also touching on something too. I mean, the treatment of these conditions once diagnosed, it's very much a therapeutic village, if you like. There's electromagnetic stimulation that you're delving into at the moment, but your past life in exercise science, for instance, may have led you to exercise life as an exercise physiologist or a physiotherapist or an occupational therapist or whatever else. And this idea of having a network of therapists or a therapeutic team is a really critical part of the battle against these kinds of conditions, isn't it?
Yeah, of course. I always say that no one therapy or treatment or approach or clinician knows everything or is the one-size-fits-all approach. I think when it comes to tackling some of the largest and most prevalent neurological diseases in the 21st century, it's going to come from combined therapies and a combined treatment approach across large teams involving clinicians, researchers, and even engineers to help to not only apply what we already know about these treatments in the nervous system to these patients, but to also research and engineer new approaches that are tailored to each particular patient. But allied health, when it comes to things like physiotherapy and occupational therapy, are really, really critical when it comes to rehabilitation after a brain injury or a disease that affects the motor parts of our nervous system. Because physiotherapy and movement, it taps into that intrinsic ability of our brain and our spinal cord to rewire, which we call neuroplasticity. Physiotherapy and exercise physiology and OT doesn't just target the muscles like what we think, it's actually changing some of the properties in our nervous system as well when a patient undergoes something like physiotherapy.
So making it even more critical to have these kinds of services accessible in one place, or as many of them accessible in one place at one time. I mean, if you think logically about this. If you're someone who is suffering with your mobility as a result of your multiple sclerosis, getting yourself to the physiotherapist and then to your neurologist and then to your dietitian and then getting to your exercise class or whatever, your hydrotherapy.
Becomes a full-time job, doesn't it?
Becomes a full-time job, and that's why it's, look, and I hope I'm not letting the cat out of the bag too much here, but I know Bond, beyond your contribution in the research space, is really excited by the opportunity to work in what's called the neuro wellness space. So literally creating a one-stop hub for patients to come and visit, where they can get their dietary advice, their physio advice, psychological support, even in addition to perhaps popping down and seeing you, Jacob. And anyway, it's a watch this space scenario involving Dr. Neil Chapman over at our building in Robina, and I know that a memorandum of understanding has been signed off on, and work is tumbling forwards with Bond University and Multiple Sclerosis Queensland, MS Queensland too. So your research comes at a particularly momentous time for the university.
Yeah, I think Bond University is in a really exciting place at the moment with MS Queensland, and it will be fantastic if something comes together with that. I think anything that increases adherence to treatments and going to clinic visits and stuff like that is only going to be better for the patient in the long term. I think moving forward, universities have a unique opportunity to best bridge the gap between teaching, clinical work, and research. And I think Bond could be a leader in the space potentially when it comes to MS teaching or education or public outreach, research and developing novel therapeutic tools, and then also the standard of care at the moment, seeing medical doctors, GPs, physios, OTs, because we have fantastic physio school, fantastic medical school that I work in here at Bond. So there are really, really talented, bright, enthusiastic, motivated people here at Bond that could all have a part to play when it comes to the MS space, I think.
Real life teaching the teacher, by exposing them to real life scenarios where people have real life outcomes. It's kind of ideal. So yeah, the idea of a neuro wellness hub here at Bond, I think it's pretty exciting.
It is very exciting.
Much needed thing. I've quoted all the numbers already. Good luck with your research. We'll pop in the show notes ways for people to get in touch with you if they want to be a part of your trial, which I'm sure they will. But good luck with it. Stay in touch with us and keep us updated. I'm curious to know what you find in the long run.
Great. I'm very excited as well.